Welcome to part 2 for section 4A on applications of trigonometry. So to begin with, we're going to be looking at the navigation problem. Okay, so it says a U.S. Coast Guard patrol boat leaves Port Cleveland at an average is 35 knots or nautical miles per hour, traveling for 2 hours on a course of 53 degrees, and then 3 hours on a course of 143 degrees. What is the boat's bearing and distance from Port Cleveland? Okay, so when we say bearing, we're talking about from north. So there's these vertical lines here, those represent north. And so when we say a course of 53 degrees, we're going 53 degrees from that north. Okay? Okay, and then 143 degrees from that north later. All right, so the first thing we need to do is understand that we need to talk about distance equals rate times time. Okay, because they give us a rate, this is a rate of 35 knots or nautical miles per hour, and a time of 2 hours. Okay, and what that's going to do is it's going to give us this distance for the first part of the course, or the first part of our trip here. Okay, so I'm going to call that D1. So the rate is 35, the time is 2 hours, that gives us 70. So this distance right here is 70 miles. Oops. Let's try that again. So this is 70 right here. Okay, so then we're going to do the same thing for the second part of the course. We went 143 degrees due north, and so we did that. It's still 35 knots, but this time we're going for 3 hours. So that gives us 105 miles. So this is 105. Okay. So the question is asking two parts. It wants us to find the bearing and the distance that it is after these two. So right now it's at C. Port Cleveland was where we started at A. So the distance is easy. The distance right here, well, first we should address why this is a right triangle. You could see from the picture that it is indeed a right triangle, but why? Well, beta right here is 53 degrees. And that's because of alternate interior angles. It's the same. Alpha is going to be 37 degrees because we got a 180 degrees right here, and then we subtract that 143. Okay, so 53 plus 37 does indeed give you 90 degrees. So this is a right triangle. So to find this distance here, we're going to use just the simple Pythagorean theorem. Okay, 70 squared plus 105 squared is equal to that distance squared. Hopefully I don't have to teach you how to do the Pythagorean theorem. All right, we square the 70, square the 105, add them together, and we get a sum, and then we take the square root. Okay, so I'm just going to skip over all that part and tell you that the distance is 126.2 miles. Okay, so that's our distance. So we got that part. So now let's talk about the bearing. So the bearing, if I just sort of sketch out this triangle, here's north. We know that this angle is 53 degrees. Okay, so our bearing is going to be from 53 degrees all the way down to that line. And so we need to find theta. If we can add theta to 53, we can get the bearing. Okay, so since this is 105 and this is 70, we can use trigonometry. We can use tangent. So the tangent of theta would be the opposite, 105, over the adjacent, 70. So I'm going to need to use inverse tangent to get the angle. And we are working in degrees, so make sure to change it from radians if you're in radians. Okay? So then calculator buttons, push, push, push. We get that this is about 56 degrees. Okay, that's this angle right here. We add to that the 53 and we get the bearing is about 10, let's see, 53 plus 56 is 109 degrees from north. All right, let's go ahead and take a look at a couple of problems with harmonic motion. Okay, so harmonic motion is any motion that kind of repeats back and forth over like a midpoint. Okay. All right, so we're going to start by looking at a piston, and then we're going to look at the spring problem. Okay. Okay, so with the piston, we have this diagram here. All right, we have the radius, okay, of the wheel is A, and that's going to be your amplitude because pretty much how far you can go is it's going to rotate around. You kind of need to see an animation of a piston to see kind of why this all works. I'm going to leave you to Google that. Okay, then we have this W looking thing, which is omega. Okay, omega has to do with the frequency. Okay, so if we take omega, divide it by 2 pi, a full circle, you're going to get the frequency, which is the number of oscillations per unit of time. Okay, so let's go ahead and look at our problem here. In a mechanical linkage like the one shown in figure 4.94, which is the one that you see in this is 4.94. Okay, a wheel of 8 centimeters, 8 centimeter radius, turns with an angular velocity of 8 pi radians per second. Okay, there's one thing I forgot to mention here. For simple harmonic motion, we're going to use this formula for the piston. And it really has to do with, if you think of cosine, where cosine starts, it starts at the top. It starts at 1, right? If you sketch a graph of cosine, cosine starts here, goes down and up. Okay, and sine is going to make more sense with a spring, as we'll get to in the next part, because the spring will start at nothing and then we let it drop and then it bounces back and forth. So it's just really about where it starts. That's the only difference between sine and cosine, right? Because sine would start here, cosine starts here. Okay, so we're going to use cosine, but we're not at that point yet. So first question is, okay, we got a wheel of 8 centimeters. The radius turns at an angular velocity of 8 pi radians per second. What is the frequency of the piston? Okay, so the frequency, remember, is the number of oscillations per unit of time. So if it goes 8 pi radians per second, okay, all you need to know about that one is how many full circles is in 8 pi. Okay, 8 pi divided by 2 pi gives you your frequency of 4. That's 4 circles. Okay, so the answer to that is 4. Okay, what is the distance from the starting point t0 exactly 3.45 seconds after starting? So the first thing we're going to do is I'm going to write an equation, d of t, the distance at a given time. Okay, and we're going to use cosine, and I should not have highlighted that in yellow, but let's see, a is the radius is 8, that's a right there. Okay, and we need the omega, or w. Okay, so remember this formula right here. Omega divided by 2 pi is the frequency. We already have the frequency is 4. So omega divided by 2 pi is 4. What's omega? Well, if you look over here, you can see it. It's 8 pi. Or just multiply both sides by 2 pi. So omega is 8 pi. Okay, so our equation is going to be 8 times the cosine of 8 pi times t. Okay, so we're going to use this to find the distance at the starting position, which is 0, and then the distance after 3.45 seconds. So we're going to find d of 0. Okay, so 8 cosine of 8 pi times 0, which is just going to turn into 0. So the cosine of 0 is 1, right? So this is 8 times 1, which is 8. So that's our distance to begin with. Okay, which I guess we're in centimeters. All right, so now we're going to find the distance after 3.45 seconds. So we're going to plug in 3.45 for t. So 8 cosine 8 pi times 3.45. So this is just all completely done in your calculator. Okay. Make sure it's in radians mode. We are in radians now. Calculator, push, 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 buttons, buttons, buttons. We get 2.47 centimeters. So then finally, to answer the question, we want to know the distance from the starting position to after 3.45 seconds. We're going to just subtract. So we're going to take 8 minus 2.47. It's about 5.53 centimeters is your answer. Centimeters. Okay. Another type of harmonic motion is the spring example. Okay, imagine we have a spring and there's a mass at the bottom, okay, weighing it down, and it gets dropped and it goes bouncy, 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 up, down, up, down, up, down, okay? We're assuming there's perfect elasticity and no friction and no air resistance, none of that fun stuff that's going to ruin it. It's just going to go up and down and up and down, okay? So this is another kind of harmonic motion. This time we're going to use sine. Okay, so let's talk about actually, what are they asking us to find here? Let's ask the question. Okay, if the weight is displaced a maximum of 5 centimeters, so you can see it's going down 5 centimeters and then back up 5 centimeters, so sort of this is the middle. Okay, find the modeling equation if it takes 2 seconds to complete one cycle. Okay, so they gave us some key information. First of all, we're going to use A times the sine of omega t. We're using sine this time. Okay, it's going to help to sketch a graph of this. All right, so at 0 seconds, okay, we're right in the middle. So 0 seconds, you can see the weight is right in the middle, which is, we're calling that 0. Okay. And then let's see, it says that there is 2 seconds to complete one full cycle. Okay, so the way I'm going to think of this, here's 1 second, here's 2 seconds. All right, so this is time, this is distance. Okay, so one full cycle is going to look like this, one thing of sine. All right, and our amplitude here is going to be the 5. Okay, because we're going up and down between 5. So this is 5 to -5, and then back up and down and up and down. Okay, so this is 5. We need to figure out what this is, omega. All right, it's going to be really in the the period that they tell us. They tell it takes 2 seconds to complete one cycle. So that tells us the period is 2 seconds. All right, we can work that backwards to get a frequency. The frequency is how many cycles in 1 unit of time. So 1 unit of time would be 1 second. It does half a cycle. Basically, these are just reciprocals of each other. Okay? So then we could use that equation, omega over 2 pi is equal to the frequency of 1/2. Okay? Cross multiply 2 omega equals 2 pi, divide by 2, omega equals pi. Okay? So that is the thing that goes here. Putting it all together, we get the distance is 5 sine of pi t. And we are done.